If you really want this to not happen, you need to show up and be prepared. You can write out your question on a note card, and you can just read it if you get nervous. If you want a question, give it to me. I'll take it up there and say it, okay? But we want to show the town board, the planning commission, that we're involved in this. This is local government at its best. And the simple solution is don't violate the 20-year comprehensive plan. A lot of people spent a lot of time developing that. This gentleman right here, Roger Miller, was our town chair. Take notes. We want the language from today to get into letters for our elected officials. The town board makes the final decision, not anybody else. Those 5 people. And if you know them, call them and talk their ear off, okay? Roger, thank you very much for coming.
So I'm going to focus solely on surface and groundwater. Now, of course, all of our natural systems are very much functionally related to that. Everything from our forests and wetlands and ecosystems and environmental corridors to our roads and stormwater runoff and how we manage that, to what is vital also in the town of Wilson is our agribusiness, because not many people in this room never eat food. So I'm going to really go right to some factual basis because some people aren't fully aware of exactly what happens with surface and groundwater. And our first little slide here is from one of the oldest USGS maps that we produced in the 40s, which is our most generalized surface soil map. And these are the soils that are really exposed at the surface. The green color represents clayey soil that, in this area of the state, has been loaded and compressed by tens of thousands of feet of thickness of glacier, so it's very dense. This is what it's like typically below 10 feet depth. It's not weathered. It doesn't have the effect of many roots, and it doesn't have the fissures and water absorption capacity that the upper portions of the clay have in our plow zone and in our weathered zone, whether it's in farm fields, under meadows, or in forests. The yellow soils that we see to the west in Sheboygan County are predominantly silty sand, silt, interbedded some places with clay. And the almost white appearance, which on the original is pink, are quite clean, meaning not much silt work and no clay, soils that are sand and gravel, where water can infiltrate very quickly. Now, in the town of Wilson, we have one special anomaly that is the cause of our unique little environment along the sandy beaches and dunes where some of us live, and the Kohler-Andre Park and the Kohler property. And this sandy soil is because about 4,500 years ago, the lake was about 12 feet higher, and the beach was along the edge of the clay zone. It suddenly dropped 4,500 years ago, and that left some sandy nearshore beach, which blew up into the dunes that comprise the Black River neighborhood, comprise the Kohler property, and comprise Kohler-Andre State Park. And under several inches of topsoil, anywhere from just a few inches if you're on the top of the wooded dune right next to the lake, to sometimes as much as 18 inches or 2 feet as we get a little bit west toward the Black River and its marshes, where we have some organic topsoil. All of the soil in this zone is just old beach sand. And the undulations that we see in the forest are old dunes that used to have dune grass but now have forests. Now, if we zoom in closer, let's orient ourselves a little bit. Let's see, my house is here. Here's Timberlake subdivision. Here's Lake Park subdivision. Here's South 12th Street. Here's County Trunk V coming into the park. The subject property under the conditional use permit is right in here, this forest. That old beachhead that I talked about is right at this transition where we drop down from these red clay lands, which we see in the farm fields, to sandy soils here. And that gives rise to a unique surface water feature. As we look at any topographic map like this USGS example, as we look north in Manitowoc County or south in Ozaukee County that lack this sand, we see that all the little creeks and streams and rivers flow directly into the lake, just as Sheboygan River does, because Sheboygan River has a large tributary area going back well west of the Sheboygan Marsh. But these tiny little tributaries that become the Black River are a small enough amount of water that draining off the highland now drops into our marsh, and you'll notice in between rainfall, we often see no water velocity at all in the Black River, which is really a creek, at any of our road or bridge crossings. And that's because the water that has been flowing and gets stored in the wetland is slowly seeping through this sand layer that's overlying this clay, continues down below the sand. We have sand on top of the clay, so the surface water drops in, goes through the sand, and is slowly seeping to the lake. So that gave rise to the unique features. Where forests didn't protect wind, we built up the big sand dunes. Where forest quickly succeeded over dune grass, the dunes didn't grow as much like in these neighborhoods. Now we're going to jump to sort of a famous old figure that I love that appears in almost all of Sheboygan County's atlases that began being produced in the late 1800s. And this is one of our earliest but really quite thorough geologic interpretations for its time that was done, I think in the 1940s. And this is a cross-section going all the way from Lake Winnebago to Lake Michigan, but its vertical scale is greatly exaggerated. Each one of these increments is just 500 feet. So in other words, this is 1,000 feet, but each one of these increments is 10 miles. So there's about 100-to-1 vertical to horizontal exaggeration here, and the reason a geologist does that is if he drew it one for one, we'd see a whole bunch of thin little lines all together right here, and you couldn't tell them apart. Now, the clayey zone that we saw in the first figure with that green clay, which outcrops throughout most of eastern Sheboygan County, is this zone. That tiny little pink stuff at the beach is too tiny to appear on this map. Those yellow zones that were more pervious soils back in the county, and I didn't include the little pink areas, overlie clay, but a lot of those coarse materials directly overlie our limestone bedrock. Now, this particular bedrock is more commonly called dolomite, and I'll explain the difference later on, but this limestone that is about 100 feet deep under our town of Wilson rises up, the surface of it rises up a little bit, so it's the same bedrock feature that you see at North Point, also the same bedrock feature that forms the Sheboygan Reef just inside of the North Point navigation buoy, and of course is also the same limestone outcropped in the Sheboygan Quarry that was mined from late 1800s through early 1900s. And this is called the Niagara Dolomite in more contemporary terms. It has that name because this same rock is the ledge rock that forms Niagara Falls. And it was the result of small organisms dying in inland seas and seas during the Silurian phase of geology, which was about 420 million years ago. And it's underlain by a less pervious zone that's a shale zone, and then a more pervious sandstone zone. Now we're going to jump to a bit of interesting Sheboygan County history. The fountain, the rather famous Fountain Park well, is about 1,270 feet deep. So it was in place at the time this geologic cross-section was drawn, and it draws water from fractures in both our Niagara Dolomite. Water really doesn't flow through this zone. This zone yields a little water, but the St. Peter sandstone yields a lot of water. But that water is millions of years old, so it's pretty high in dissolved solids. So by contemporary standards, we would regard the Fountain Park water well as very poor water quality standards for drinking. In other historic contexts, people came from far and wide to get gallons of this stuff to take home to drink. Our water, almost all of the wells in the town of Wilson are within the top 200 feet of the dolomite. Very few of them go deeper. There are still a few old sand points in the dunes along the lake. Not many of those are left. Now, so the way water works as a cross-section is, even though there's mostly clay in the Fond du Lac Basin, farther in other places the St. Peter sandstone outcrops and gets recharged, but it takes millions of years for this water to get this far east. The water that we get out of our wells here in the upper part of the dolomite, most of that water soaked into the ground in the Kettle Moraine area, and on the average probably took about 2,000 to 4,000 years to get to our wells, because the gradient or driving force of that water from this elevation to this elevation is only a couple hundred feet in 20 miles, which is a pretty low gradient. So that's our overall picture in the biggest sense. Now, up in those yellow conductive zones, they're below a water table. Water is just flowing through the pores in soil ever so slowly. Even in sand soils, through our sand dunes for that shallow system, movements of water might only be in inches per week or inches per day. Down in the dolomite, and what we don't have here is our clay zone sealing off the dolomite in this particular picture. Water is moving through quite small fractures in that dolomite bedrock. Most of the fractures that our well boreholes intersect are less than a pencil lead in thickness. So our boreholes have to cross a number of those fine fractures to get enough yield of water for it to be a useful water supply well for us. So water is not moving in the ground in cavernous rivers. It's running through small fractures. Now, there are parts of the world that water does run through cavernous rivers, but that's in areas that the limestone was not glaciated. So it had shallower limestone that had millions of years of weathering and solution channels, as we have in other parts of the country and throughout most of Central and a lot of South America, and southern parts of the United States, where there are truly underground rivers flowing. That's not the case here, because our glaciers scoured off all that weak rock and left us with quite firm, competent bedrock.